Okay, in this session we want to look at the quotient of two complex numbers in polar form. If we have the first complex number z is the modulus of z times quantity cosine of alpha plus I times the sine of alpha, and if we let w equal the modulus of w times the cosine of beta plus I times the sine of beta, then we define the quotient z over w as the modulus of z divided by the modulus of w times quantity cosine of alpha minus beta plus I times the sine of alpha minus beta, provided the modulus of w does not equal 0 or w does not equal 0. To divide two complex numbers in polar form, we wanted to divide the moduli and then the angles or the arguments subtract. So for example, if we let z be equal to 6 times the cosine of 75 degrees plus I times the sine of 75 degrees, and if we let w equal 2 times the cosine of 45 degrees plus I times the sine of 45 degrees, then z divided by w is equal to 6 divided by 2 times quantity cosine of 75 degrees minus 45 degrees plus I times the sine of 75 degrees minus 45 degrees and quantity, and simplifying that as 3 times the cosine in 75 minus 45 is 30 degrees plus I times the sine of 30 degrees. Our second example is if we do not have the numbers in polar form to begin with, we can just still divide. We have z is equal to the square root of 2 minus the square root of 2i, and let w equal 1 minus I. And here the goal would be to write each in polar form and then use our nice result up here where the moduli divide and the arguments subtract. We want to find the modulus of z is equal to the square root of the square root of 2 squared plus negative square root of 2 squared, and that will simplify as the square root of 2 plus 2, which simplifies further as the square root of 4, and the square root of 4 is 2. So the modulus of z is 2. Likewise, we can find the modulus of w. That will be the square root of 1 square plus a negative 1 square, and simplifying that as the square root of 1 plus 1, which is the square root of 2. So the modulus of z is 2, and the modulus of w is the square root of 2. Next, we want to find the arguments of each of those complex numbers. If we look at the first number z, here's the complex plane, and the square root of 2 comma negative square root of 2 would be down here in the fourth quadrant. So there's our angle. Tangent of alpha is equal to the imaginary part of z divided by the real part of z. Tangent of alpha is negative 1. That corresponds to alpha negative pi fourths, or alpha is 7 pi over 4. From the polar axis to that complex number, we have 7 pi over 4. Now finding beta, we would have the tangent of beta is equal to the imaginary part of beta, which is negative 1, divided by the real part of beta, which is positive 1, and that corresponds again to the same reference angle. Tangent of beta equal negative 1 tells us beta is also 7 pi over 4. Therefore, z divided by w is equal to the modulus of z divided by the modulus of w times the cosine of alpha minus beta plus I times the sine of alpha minus beta, and that gives us z over w is 2 divided by the square root of 2 times quantity cosine of 7 pi over 4 minus 7 pi over 4, that's cosine of 0, plus I times the sine of 7 pi over 4 minus 7 pi over 4, 0 as well. So there's our number in complex form. 2 divided by the square root of 2 can simplify as the square root of 2, and then we have the cosine of 0 plus I times the sine of 0, and that simplifies the cosine of 0 is 1 and the sine of 0 is 0. So for these two complex numbers, z divided by w is just going to be the square root of 2 in standard form. And in polar form, the square root of 2 times the cosine of 0 plus I times the sine of 0. Now if we remember doing the problem in standard form, we would have to take the square root of 2 minus the square root of 2i divided by 1 minus I, and to divide complex numbers in standard form we would go about multiplying by the conjugate, 1 plus I over 1 plus I. And when you do that multiplication in standard form, multiplying those two straight across, you will end up with, at the end of the day, the square root of 2.